In this lecture, I want to talk about the price elasticity of demand and what that means, what it is in terms of the economics application, and then how we can use calculus and derivatives in particular in order to determine when price is elastic. So an elastic price means that the price is that demand is sensitive to price. In other words, if the price on something increases, you'll see a significant drop in the demand for that product. Or if there's a significant drop in the price, then you might see a big increase in demand. So maybe an example of a commodity or a product that behaves that way is maybe something like the latest smartphone. There might be a high demand, but only at a given price, right? Like if the price on that item were to drop quite a bit, you might see a lot of people go get that new smartphone. But if the price were really high, then you would probably see people just kind of stay with the phone they have or buy something a little bit cheaper. An example of something that's not elastic, we call it inelastic, is gasoline prices. So whether, it's not like if the price goes way down that everybody's going to stock up on gasoline. Some people might make trips that they otherwise wouldn't make. But for the most part, people put a certain amount of gas in their car every week. And whether the price is up to $10 a gallon or down to 98 cents, the amount that they're going to buy isn't going to change very much. So the demand for that is not going to change very much based on the price. So that's an example of something that's inelastic. So what we want to do here is say, well, how can we build a mathematical model of the price elasticity of demand? So the first thing is to understand what we're actually looking at. So we're looking at the rate of change of demand as a percent with respect to the rate of change of price as a percent. All right, so it's the rate of change of demand with respect to the rate of change of price. We want to know how changes in price and changes in demand are related. So that's when we end up with kind of two rates of change here. And we're going to let X denote the number of units or the demand, the number of units that would be sold at a given price, where P is the price per unit. So the way to then think about this rate of change of demand as a percent is that we're talking about delta X, which is the change in X. It's the change in demand with respect to basically what the current demand is. That gives us a percent. It's the part over the whole, right? The change with respect to the current demand. And then likewise, for the rate of change of price as a percent, we're looking at delta P over P. All right, the change in price with respect to the given price, the current price. So we can rewrite this just with what we know about fractions as delta X over X. Dividing by a fraction means multiplying by the reciprocal, so we have something that looks like this. All right, and then since these are just multiplied, we're multiplying the numerators, multiplying the denominators. It doesn't matter what order we have that in, so we could just as well write that delta X over delta P times P over X. All right, which again, because these are multiplied, it doesn't really matter which one comes first. We could have P over X times delta X over delta P. But then using this idea of dividing by a fraction is the same thing as multiplying by the inverse, we can also say that multiplying is the same thing as dividing by the inverse, so we would end up with P over X over, and we take the inverse here, so we have delta P over delta X. All right, so what we're looking at, so we end up with something that's kind of nice because we have P over X over delta P over delta X. But what we're looking at here then is the price divided by the number of units, and this is the change in P with respect to X. And when we talk about change in calculus, we basically are talking about the derivative, so we can further rewrite this as, and we're going to say this is an approximation because this is like a small change, but what we're talking about when we use the derivative is instantaneous change, right, for one given point of price and demand. So we're going to end up with P over X over dP dx. x, which is the derivative of price with respect to demand. Okay, and this quantity is denoted with the Greek letter eta, which kind of looks like that. Not great at drawing etas, but that's kind of what you'll see denoted in terms of the price elasticity of demand. So we say that demand is elastic, and what we mean by elastic is that it's sensitive. So the demand is sensitive to price when eta in absolute value is greater than 1, and that demand is inelastic when eta is less than 1. And then finally we say that that the demand has unit elasticity. Unit basically meaning 1, right? When eta equals 1. And basically what this means is that like a $1 drop in price would result in selling one more product, or a $1 increase in price would result in selling one less product. So basically revenue is unchanged there because it's kind of a one-for-one exchange in terms of the price and the demand. So this is kind of an important point because this is, when you get that point, it's almost like a point of equilibrium. Here you can certainly sell more by dropping the price, or the demand will drop off if you raise the price. Here, changing the price doesn't really affect the demand. So in terms of revenue, let's talk about what this would look like in terms of revenue. So if I wanted to draw just kind of a sample revenue, so revenue might look something like this. All right, so here at the peak point, all right, that's our unit elasticity. So this is revenue with respect to number of units sold. And over here we know that the derivative, because this is an increasing function, we know that the derivative with respect to x is positive, and this is where demand is elastic. Revenue is increasing when demand is elastic. All right, and then over on this side we know that it's a decreasing function. As revenue goes down, we know the derivative will be negative. This is where demand is inelastic. So if we can find these points when eta equals 1, when it's greater than 1 and less than 1, we can say something about revenue based on the elasticity of demand. Okay, so that's kind of your overview in terms of all the symbols. Let's look at a specific example so we can kind of make more sense out of this. All right, so here's a specific example. We have a specific demand function that we're looking at. Let's see if we get this centered on the screen here. Here we go. Okay, so the demand for a product is 36 minus 2 times the square root of x. And this is for, and then, x is the number of units. So this is for a number of units being between 0 and 324 units. And then P is our price per unit. So a couple things we want to do here. First is to determine when the demand is elastic, inelastic, and of unit elasticity, and then use that to describe what's going on with the revenue function. So again, just a reminder, eta, that's P over X over dP dx. So the first thing to find here is P over X. Well, here's P. So P over X is going to be 36 minus 2 square root of X over X, which equals 36 over X minus 2 square root of X over X. Well, we can think of X as the square root of X times the square root of X, right? Because the square root of X squared is just X. And so we could simplify this to be 36 over X minus 2 over the square root of X, right? Because if this is square root of X times square root of X, then it cancels with one of those and leaves me a square root of X in the denominator. Now finally, we need also dP dx in order to compute the elasticity of demand. So looking at this, then our derivative, 36, would go to 0. You can think of this as x to the 1/2. So when we take the derivative, we would multiply by 1/2, giving me -1, x to the -1/2, right? Which is the same as -1 over the square root of x. Okay, so now put this in here, and we're going to take this and put it in here. So eta is going to be 36 over x minus 2 over the square root of x over -1 over the square root of x. And I'm going to again multiply by the reciprocal here. So I'm going to have 36 over x minus 2 over the square root of x times negative square root of x. Alright, so I distribute that to each of these using the same idea where the x is the square root of x times the square root of x. I can cancel one of those with that one, and I'm going to be left with, and then I have this negative also, so I'm going to have negative 36 over the square root of x. And then these will cancel, the negatives will give me a positive, and I'll have plus 2. Okay, now I want to know when this in absolute value equals 1. So there's two ways that can happen. Either, well, moving this up a little bit here, either I could have negative 36 over the square root of x plus 2 equals 1, or I could have that negative 36 over the square root of x plus 2 equals -1, right? If this in here equals 1 or -1, then I'll have the equation that I'm looking for. Okay, maybe I'll just back this out a little bit so we can see the whole page there. Okay, so continuing then with this, this means I could subtract 2 from both sides. I'll end up with negative 36 over the square root of x equals -1, which is the same as saying that the square root of x equals 36. Right? We see if the square root of x was 36, I would end up with negative 36 over 36, which is -1. So here I can square both sides, and I would get x equals 1296. But notice, back up here at the top, that's outside of our range. So this is not a point that we need to keep track of. All right, let's see what happens over on this side. So here I subtract 2 from both sides. Now I've got negative 36 over the square root of x equals -3. Well, that would mean if I take negative 36 and divide it by 12, I get -3. So that would mean that the square root of x would have to equal 12. So that x, after we square both sides, would be 144. And that is within our range here. So this is the point where we have unit elasticity. We have that eta in absolute value is equal to 1. But we just have a little bit more work to do here, right? We need to determine when the demand is elastic and inelastic as well, which will likely be on either side of this. We just have to figure out which side of it is it elastic and which is inelastic, and then use this to talk about what's going on with the demand or with the revenue function. Okay, then. So we know that in absolute value, eta equals 1 when x equals 144. We also know that this price is good for values of x between 0 and 324. So this breaks up our interval into 0 to 144, and then 144 to 324. All right, whoops, 324. All right, because we know that it's going to be of unit elasticity at when x equals 144. And on one side of that, it'll be elastic, and on the other side, it should be inelastic. So if we go back to what we found here, right, we want to know when that's going to be, well, let's go ahead and write it here. We want to know when negative 36 over the square root of x plus 2. This was the derivative that we found. All right, and we want to know, well, we're going to pick something in between here because what we want to find out is when is eta less than 1? All right, because we know that that when it's less than 1, we know that it's going to be inelastic. And then we also need to find out when eta is greater than 1 because that's when it'll be elastic. So if I take this expression and pick something in this interval, if I end up with something that's greater than 1, it's elastic. If I end up with something that's less than 1, it's inelastic. It should be the opposite on the other side, but we're going to check both. Okay, so let's just pick something. I want to pick something that would be easy to plug in here. So 36 would be easy because I can just say 36 over the square root of 36 plus 2. Well, that's going to be negative 36 over 6, which is negative 6, plus 2 is negative 4, and the absolute value of negative 4 is greater than 1. So in this interval, then, we know that demand is elastic. All right. Now let's just pick a sample point here. I like to pick something that's a perfect square so that when I take the square root, I end up with something that's, an integer. So let's pick 225 because the square root of 225 is 15. So plus 2, so this is negative 36 over 15 plus 2. Well, that's negative 2.4 plus 2, which equals negative 0.4. And we know that the absolute value of negative 0.4, in absolute value, that's going to be less than 1. So this is where we are inelastic. So to be clear, we're elastic on this interval. Price or demand are elastic. Demand is elastic with respect to price. And then here, we're inelastic. So we're looking for open intervals. We know, so let's just talk about this in terms of revenue also. Okay, so, because I think that will help us to see what's going on here. So again, we have revenue. This is number of units sold or produced. Okay, so our function might look something like this. All right, where at this peak, we know we're at 144. All right, so we can see, we know that when price is elastic, that's when revenue is increasing. So we can see that in this interval, 0 to 144, we know that revenue is increasing, and then it's decreasing when prices or when demand is inelastic. So over here from 144 to 324, this is where its revenue is decreasing. So we can kind of think of this unit elasticity as the point at which revenue is maximized, and it'll be increasing when the demand is elastic, and it will be decreasing when it's inelastic. Finally, we could also figure out what that maximum revenue is, because we know that revenue as a function of x is number of units times the price per unit, right? And we know that we found the number of units to be 144, and if we go back to our original function was 36, the price as a function of demand. Well, we found that to be 144. That's the point where we have unit elasticity. So we can put in 144 here for P. So I've got 36 minus 2 times the square root of 144. All right, that's going to be 144. Well, the square root of 144 is 12 times 2 is 24, and 36 minus 24 is 12, and then that will give us 1728. So this would be our max revenue. Our price would be 12, right? Because we put in 144, and at a demand of 144, we don't know what the units are. We could say maybe at $12, we're going to sell at 144, and that will give us a revenue of 1728. So that's how we. That's an example of how we might use these ideas in order to determine what's the best price, or in order to maximize the demand and then ultimately maximize revenue.